All right, we are live. We are live and we are recording. So you guys can see my stuff, right? Yay, I agree. Yay, here we go. So I'm just going to repeat this one right here. Forget about everybody else. So first things first is run the appropriate descriptives in SPSS for the variables. We're going to go to, we're going to go to our data set. We're going to go to Analyze, Descriptive Statistics, Frequencies. We're going to put the variable, let me reset this. We're going to put the variables that we want in there. So it's going to be not gender, it's going to be age, collectivism, forbearance, oops, damn it, hold on. Age, collectivism, forbearance and support. Click that. So it automatically displays frequency tables, which is, how many in each. Don't even worry about that. Statistics, you tell the computer what you want. You want the average of each one, the median of each one, standard deviation, the variance, the range, the minimum, the maximum. You really don't care about the standard error of the mean at this point. And do not click percentiles for this one. Let's see what it looks like. Bam. And this is how you get the first table, right? So the frequency tables, these are the percentages, like how many people were 22, 10%, how many were 23, 15%. But I don't think he wants those. But you know what? Let's put them in there just in case. I'll leave it up to you guys. Because that percentile, the percentages of each one, that's too much data. That's really, really too much data. So there's the original ones. So these are the percents. Again, I'll leave it up to you guys if you want to leave them in there. But here's the main one, and this is the statistics one. Okay. Now watch, let me see if I can't. This is almost APA formatting in itself, right? Let's take a look at it. Where'd you go?
I never printed, I just used something completed it.
Boom, okay, there, that's that. So what we're gonna do is, I'm gonna try to recreate this in Excel. Give me a fresh one, and then we'll paste it in there. Beep, 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 beep. So that's APA formatted. Let's make this a little bit bigger here so it stretches out there. Very nice, very nice, very nice. See what I'm doing? I'm making the rows all the same width, height, or whatever you want to call it. Looks prettier. And actually, I think the first variable is supposed to be on the left-hand side, but that screwed everything up. So let's Control Z and, oh, you stupid thing. Hold on a second.
Someone asked how come we're not including gender.
Because gender is a categorical variable, and in categorical variables, the mean and the standard deviation means nothing. It means absolutely nothing. Okay. So an example is take ethnicity, right? 1 is white, 2 is African American, 3 is Hispanic, 4 is Asian, 5 is Pacific Islander. If you took an average, it would probably be something like 2.7. What does that mean? What does that mean? It doesn't mean anything. So that's why I left gender out. But now in the sheet, I put it back in for you guys.
So for gender, could we do like, I think that's what you did, right? The frequency, and then it just sounds like the percentages. Can we do that?
Yeah, you sure can. In fact, that's a good idea. So for gender, I would probably do, now these percentages, they don't mean much. I'll be honest with you, they don't mean a lot. But now let's do this. We'll go back to Analyze, Descriptive Statistics, Frequencies, and this time we will just do gender. And it should tell us how many males and how many females. But again, we don't need the mean, don't need the median, don't need that, don't need that, don't need that, don't need that, don't need any of that stuff. But it should tell us how many are in each. So percentiles, nope, no percentiles. Let's see what that looks like. There it is right there. So gender, 60% female, 40% male. And homework assignment. So I'll put those at the top of these things. Frequency table. So that one's good. The rest of these, Again, I don't think your teacher. Oh, it's a she, right? I don't think she wants this, right? How many people were 51 years old? One person. I don't think that's what she is after when it comes to percentages. But again, I'll leave that up to you. She'll tell you one way or the other. Right. And, okay, so you want this format up here, probably. See, it takes more time to put these things in the right formats than it does to actually do this stuff. And that's something I really dislike. I don't like it. I just don't like it. I like numbers. I don't like all this other stuff. So now we could do this. So we could do variables. So it would be male and female, right? Gender. Capital G. And it would be female. This would be gender. And this always has to be, boom, okay, so variable. No, this is just gender, right? Gender again, and this would be male, or this would be female. This would be male. And we don't need these two. And we will delete those cells. Delete those cells. We want them rows out of there. And so we want, what do we want? Frequency. That's actually in as frequency, right? So 12 and 8. And percent. So 60 and 40. And don't need the rest of this stuff. The rest of that stuff is you don't need. So let's just get rid of the rest of it. Delete columns, yes. So, not very pretty, but APA formatted, yes, sir, Bob. Kind of plain Jane, if you ask me. You know what? I'm going to let you guys worry about the formatting into tables and stuff, okay? Again, use this as a format and then make all the data fit into it. Where to go? 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 Use this. This is an excellently formatted, this is perfect APA formatting. Got to have the big black bars and everything. But again, this is not my strong suit, but you guys are more artistic than I am. All right, here we go. Also report the descriptive statistics in a paragraph describing the information on the table, including a sentence on whether the assumptions of normality were met for, oh, okay. So we have to check out these things and see if they're normal. So let's take the first one. Let's take age. All right. The variable of age, and in parentheses you do the mean, which was 29.05, comma, standard deviation is 8.59. And I believe these are italicized was or was not normal. And then we're going to go ahead and run it through. We're going to run these for normality right now. So back to here. So to check for normality, there's more than one way again, but we're going to go to Analyze, Descriptives. We're going to go to Explore this time. And we're going to kick in Age, Collectivism, Forbearance, and Support. Now, when it comes to checking normality for ordinal variables, they violate normality all the time. That's part of why they're ordinal variables. Okay, most people would check like a 1 or a 5. They rarely pick 3 all the way across. That's what that means. If an ordinal variable is normal, that means everybody picks 3, which is not what you want. You can't really do that. So to check for normality, you go to Analyze, Descriptives, Explore, click on Statistics, and this is a default. It's going to give you a bunch of statistics you really don't need. But plots, this is your money. Unclick the stem and leaf, click the histogram, but this one right here in the middle is the most important. Normality plots with tests. It's going to give you a mathematical formula, actually a mathematical it runs the math for you, and it will mathematically tell you if in fact it is normal or not. And that test is called the takes a while to eat a chocolate. There you go. So here they are, right? Nobody's missing. Here's descriptives of age. We already knew this, right? The mean, the standard deviation, the median, etc., etc. We don't really need this box. This is your money box right here. Age, because this sig value is less than 0.05, that means you violated the assumption of normality. So age violated the assumption of normality. There's the histogram. It's easy to see that it violated normality. And we don't use the normal QQ plot anymore. And we don't use the other QQ plot anymore. But here's a stem plot. I'm sorry, this is a box plot that shows you that you have some outliers in age. So number 6 and number 20. Let's see what number 6 and number 20 were on the data sheet. So number 6, age 49, he's an old guy. And 20, 51. So you got 2 old guys on here that are acting as outliers, and that's what's making it not normal. So if you got rid of those 2 guys, you might have a normal data set, but you don't always have to do that. So here's collectivism. It's supposed to shape a bell curve, and that really, oh my God. You could, with with the stretch of the imagination, that doesn't look too bad. Right, this is relatively symmetrical. It's not perfect, but it doesn't have to be perfect in order to be considered normal. So here's one for forbearance. This is getting closer to normality. Again, it's not perfect. And again, this looks pretty symmetrical, so it's probably normal. And the last one is, you could kind of see a bell curve in there, but again, it's kurtotic. It's got too many high points on it. But it doesn't matter what the picture looks like. We're going to go by this box, the Kolmogorov-Smirnov box. So what I'm going to do is I'm going to cut and copy all of these things and put them on the page for you, and then see what your teacher wants. Now, when you guys are sending this thing in, don't all send in the exact same thing. She's going to get mad. She's going to yell at me. Okay? So just use your common sense, please.
So it is normal?
Say that again.
So it is normal, like the normality.
Yeah. Again, don't care about the pictures. The pictures can be misleading. always go by the mathematically calculated, either the Kolmogorov-Smirnov test, this guy, right? Either these guys or these guys. One is for a large sample size, one is for a small, but depending on which book you read, it kind of flip-flops. But now they both agree that age violated the assumption of normality because the significance on both of these is less than 0.05. So that's the only one. So we're going to write it up like this. The variable of age was, okay, so it violated the assumption of normality. So we might as well put this in here. Right, according to the test of normality. All right, what just happened here? Come here, you silly thing. All right, according to the Kolmogorov-Smirnov test of normality, the variable of age, and again, here's the mean and standard deviation. That I know is APA format writing. Whenever you mention a variable, you're supposed to put the mean and the standard deviation, just like this in parentheses. Violated the assumption of normality. Now, the K, so a lot of people will write this. KS stands for Kolmogorov-Smirnov. You put the test statistic, it's 0.294, comma, and then you put the p-value was less than 0.001. You never put p equals 000. You never put that. And I think you got to put the degrees of freedom right behind that as well. So this tells you you're using the Kolmogorov, can't even pronounce it anymore, the Kolmogorov-Smirnov test. So degrees of freedom is 20, that's your sample size, and the actual number of the test statistic was 0.294, 20 degrees of freedom, and there was the p-value, okay? The other variables did not violate the assumption of normality. Now, you guys can list them out if you want. I'll leave that up to you. How's that? Right? So only age violated the assumption. And then you got all this crazy stuff. I'll just, again, I'll leave it up to you. You guys good?
Yes. Can you go over some of the stuff on the PowerPoint?
Yes. All right, submit your data file. Okay, that one's done. Okay, so we'll do PowerPoint stuff. You just let me know, all right? Whatever you guys want to do, you got me till 4:30, so you got me for another hour. Which one?
I don't know, the most recent one I sent you. I think it might have been.
I got 1, 2, 2, 3, 4, 4, 4.
Let me see here.
Now, the homework, the pictures of the book you sent me, which are very clear, by the way, thank you for that. That looks like a one sample t-test.
But for that one, we're literally just following like the directions in the book, right? So that one shouldn't be too hard.
It's not hard at all. Plus, I got more videos. I'm going to send them to you once we're done. I got a ton of one sample t-test videos by Hand Excel or SPSS on the Hawk 2. Here's Did you guys just hear that? There's a ghost in the machine. Yeah. So since we talked about normality, let's check out the normality one. Frequency distributions.
Is it the week 4 describing normality?
Yeah, that's the one. All right, a frequency distribution. Okay, so there's a ton of different frequency distribution graphs. You got your bar charts, your pie charts, your histograms, your stem and leaf plots. Basically, it just shows you how the data is spread out. Literally, that's what it means. How is your data spread out? That's what a frequency distribution is. Yeah. Okay, so a histogram is like a bar graph, except for instead of categories at the bottom on the x-axis, it's got intervals or ranges. So let's say we had a histogram of grades, right? The first bar represents A's, the second represents B's, C's, D's, F's, that kind of thing. If you were a teacher. So under the A part, the rectangle would go up to how many people got A's, and the B rectangle how many people got B's, etc., etc. So your Y category is how many how many people got an A. So a histogram, you would change that A, B, C, D, F stuff to like 0 to 20 would be the first one. 21 to 40, 41 to 60, etc., etc. So your x-axis is no longer categories; it's between values. So you would count how many people were between 1 and 20, and that would be your frequency. You would count how many were between 41 and 60, that would be your interval there. That kind of thing. That's a histogram. Now the bell curve is based on a histogram. And there's a histogram. This is a normal histogram. Relative. This is not a normal histogram. I don't know. I know what a polygon is, but I've never seen one drawn in a SPSS before. Oh, that's if you're using a line graph. Don't use line graphs. Bar graphs, you're going to use bar graphs, but they're pretty easy. You've been doing bar graphs since the 7th grade, right? Personality types, A, B, C, how many are in each one? Now, the reason we use frequency graphs, distribution graphs, is because you can look at the data in a blink of an eye, and find out who's the most, who's the least. Right? I don't even have to think about it. I can say, oh, this C-type personality is obviously the most popular, and the B-type is the least popular. That's why. It allows us to take snapshots of data. Stem and leaf we don't use anymore, but I might as well show you. So if you got a ton of data like this, right, 83, 62, blah, 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 what you can do instead of writing all those numbers out, you take the leading digits, the tens column digit, and you write them out for what you have, and then these other ones are simply the ones digits. So this 3 line 2 3 means 32 and 33 are both in this data set. So 4/26 is 42 and 46. They're both in that data set, etc., etc. So even looking at the stem and leaf plot, if you turn this whole thing 90 degrees counterclockwise, it would look like a bell curve, kind of. See that? You can also use these to see if it's normal or not. But this data doesn't look normal because the longest number is not in the center. It's a little bit off. So this whole data set looks like it's a little bit skewed. And then this is how we display frequency table. With this stuff, I strongly suggest you kind of play around with it. And if you can't find videos on the hawks, which you will, I got videos on everything. YouTube, I guarantee you, has videos on everything you will ever need to know in SPSS. Did I show you how to make z-scores yet?
Yes, yeah, you showed us last time.
Okay.
Um,
All right. Okay. How about the box plot? You guys want to know about the box plot?
that one, yeah.
All right. The box plot takes. So pretend you're a teacher and you got 5 classes, and you got 167 students, right? So one Friday you give 167 students the test, and they take the test. So you go home and you grade 167 scores. You know, a couple of people got zeros, a couple of people got 100, and everybody else got between 0 and 100. So you got this long list of variance scores, right? The scores are difference, and the difference in there is what we call variance. So what it does is it will take that score for your student, the one that is the median, the one in the middle. So in other words, there's one score where half the students scored higher and half the students scored lower. That's your median, okay? Your first quartile, this one is upside down, by the way. Normally the low scores start on the bottom and the high scores go to the top. Oh, they did have it. No, this is confusing the hell out of me. So it has 99 up here and 1 down here, but then it has high scores and low scores. You guys feeling me here?
Yeah.
This is a shitty picture. You tell your teacher not to use this picture ever again. So how it's supposed to work is the highest number is your maximum. It's the highest number in your data set. This next this horizontal line, this second one, this is what you call your third quartile. In other words, 3/4 of your data, it acts like a median, but instead of half the data underneath it, 3/4 of the data is beneath it. That's your third quartile. A median is your second quartile. In other words, half the data is below it, half the data is above it. This bottom one here, the bottom of the box, is your first quartile. 25% of your data is underneath it. It's whatever that score is from your 167 students, where 1/4 of them, what would that be, 42? 42 students would be beneath this score. That's your first quartile, and then this is your minimum. And again, I got videos on how to do it by hand, how to do it in Excel, et cetera, et cetera. So the interquartile range, nobody uses that anymore. Should I go over it?
I don't know. Do we need it?
I don't know. This is what I call saber-tooth curriculum. It's not used anymore. But let me show you how it works. So the interquartile range is the old-fashioned way of identifying an outlier. So what you would do is you would go back here. You would take your third quartile, whatever that value was, and so let's say the third quartile was there. It was like 80, and your first quartile was 60. So you would subtract the first quartile from the third quartile, the little number from the big number. 80 minus 60 is 20. So there's 20 points difference. That's the quartile range, right? 20 points difference between the third quartile and the first quartile, and then you take that number and you multiply it by 1.5. So if we took 20 and multiplied it by 1.5, that would be 30. And so any data point that is 30 points above the mean would be considered an outlier, or 30 points below the mean, that would be considered an outlier. So this one says any data point that falls between 0.15 and 0.3. So anything over 1.5, anything over 30 points from the mean or below 30 points with the mean would be an outlier. And then I don't know what this is. And 3 times the outlier? That makes no sense to me. An E means it probably means an extreme outlier. All right, skewness means it slants your frequency distribution slants. It either slants to the left or it slants to the right. Right? It's lopsided. That's what skewness is. Kurtosis, on the other hand, is it's got too many high points or too many low points. Okay? So skewness is the left or right look of your graph, and kurtosis is the vertical up and down look of your graph. And both of these have to do with normality. And these numbers, I wish they wouldn't have put them in there because that's not how we do it. Right? These I'm going to come out and say it. These are not used at all anymore. And I don't want to get into a cat fight with your teacher, so don't tell her what everything we say here. So testing of normality, this is the main one we use. We did that already, right? Right? If it's significant, in other words, if that sig value is less than 0.05, that means the data is not normal. You violated the assumption of normality. Central limit theorem. You guys know what that means?
We went over it last week, but I forgot it.
It's really easy. All you got to remember is this. The central limit theorem says, and I quote, if the sample size is large enough, and they don't give you a number, if you got a big sample size, then you can pretend that the sample mean is equal to the population mean, and you change the sample standard deviation into the standard error, which means you take the standard deviation and you divide it by the square root of the sample size. That's the standard error. So whenever you hear central limit theorem, you should be thinking of dividing the standard deviation by the square root of the sample size, because that is what we call sampling, and it's very confusing and most students forget it. That's the central limit theorem. Divide the standard deviation from the population if you got it. Divide that by the square root of the sample size. If you don't, use the sample one. For quantitative data, analyze, descriptive, explore. Again, so you can use frequencies, you can use descriptives, you can use explore. Categorical data, crosstabs. Crosstabs is a test. That's your chi-squared test. Again, these are three ways to get all your descriptive statistics. Frequencies, descriptives, explore. All right, so now she's into the one sample t-test. All right, very important. There's three different t-tests. There's a one sample t-test or a one-way t-test. There's an independent t-test or a two-way, two sample t-test. And the last one is what we call a paired t-test. Has she hit you with that yet?
I don't think we went over that yet.
All right, so I don't want to go there either until she hits you with that. So, but a one sample t-test, it's pretty basic. What you're comparing is you're comparing a sample to a stated population mean. And a stated population mean is what we call a norm or a claim, and it usually comes from an authority type of thing. Example, you wanted to check pretend you're an 11th grade teacher, you wanted to check your class's math scores against the California State average, right? So the California State of Education, Department of Education, they say, oh yeah, the average on this test was 77.9. So that, coming from, California, you're going to believe that it's accurate and true, so that's your norm, and then you would take whatever your average was for your class, let's say it's 82.3, you're going to run your 82.3 from your class through this long, ugly formula and test it against the state's stated mean of 77.5, whatever it was. Okay, that's a one sample t-test. So basically, all t-tests compare means. They compare the means of the groups. That's a test question. T-tests actually compare the means of the different groups to see if they're significantly different significantly far apart from each other. Okay. And okay, here's a major point that throw people off: a one-tailed test versus a two-tailed test. Now these are tests of significance. Significance means that the means, in this case, the means are far enough apart from each other that they can be called significantly far apart. And normally it's just, the mean should be at least 2 standard deviations away from each other. So a two-tailed test is if you don't know, you as the researcher, you have no idea if your mean is going to be bigger than the population mean. You have no idea. So that would make a two-tailed test, because your sample mean could be greater than the population mean, or your sample mean could be less than the population mean. So it goes both ways. It's called directionality. But here's how you remember if it's a one-tailed test. If you're assuming that one will be bigger or smaller than the other one, again, you as the researcher have to say, you know what, I know my class did better. Better, right? Better, more, greater than, less than. Any of those comparative type words, that makes it a one-tailed test. Now, SPSS only reports two-tailed tests, because in the real world, once you get out there and you start doing statistics for your daily bread, everybody uses t-test, two-tailed t-test, because it's a little bit harder to get significance, which makes your test that much more better. Okay, but to change a two-tailed p-value into one-tailed, all you got to do is divide it by 2. Okay. And this is how you write it up in APA formatting. The mean of age, mean equals this, and this is wrong. This is wrong. Where did you get this book? Man. What book are you guys reading? It's full of mistakes. I mean, okay, and she wants competence intervals. You guys know what competence intervals are?
No.
Competence intervals is the group mean plus or minus a margin of error, which is like wiggle room. Now, whenever you're talking about a mean of something, a mean of a sample, you're never sure if that sample mean is the same as the population mean. In fact, it rarely is. So if you take any sample and you take the mean of that sample and you think that's true for the population, that is a giant mistake. So what they do is they make this like interval to try to trap the true population mean. So a 95% confidence interval would be the mean plus a little bit of wiggle room, and the mean minus a little bit of wiggle room, and that real wiggle room is called margin of error, and it's done mathematically. But this is interesting. We never write up the confidence interval down here, but it's not wrong. It's just we don't do it here. But this mean should just look like this, M, right? And N, we don't write this. We don't. Okay, I'm rambling. I apologize. Moving on. Let's do some more. I need more numbers. This stuff is boring the shit out of me, you guys. Sorry. It was a little uncalled for. Let's do some numbers. Have you had this one yet? Week 7?
No.
How can you do week 7? It's only week 4.
Oh, no. Can you, the critical region, can you go over that? The critical region? That's just like what's under the bell curve, right?
What did you call that?
The critical region?
What, CI?
No, the critical region. Like, what is that?
Critical region. Oh, I think I know what she's talking about. Let me pull up a quick picture. Please hold. Can you guys still see my screen?
Yeah.
Good. I will take you in and we will get you a critical region. There's one right there. Bam. Okay, can you see my bell curve?
Yeah.
All right. So when you run all your crazy calculations and you get a t-score, these will, let's pretend these are the t-scores down here, okay? So the critical regions are anything, I'm gonna just make this shit up as we go here, bam, bam, bam. That is a, that didn't work, hold on a second, I want pencil, I want basic, bam. Let's change that color to red, boom. And, okay, so Control C, Control B, So if the null were true, and there was no significant difference, then your test score, your t-test or your z-test, should have fallen between -2 and +2. In other words, any t-score, any test statistic that fell between -2 and +2, anywhere in here, means that the null was probably correct. Got it? If you get a t-score, any kind of score between -2 and +2, roughly, okay, that's a rule of thumb. It depends on your sample size and a couple other minor things. But the general rule of thumb, and this is the 95% confidence interval rule, this is the same as the empirical rule, that if the null were true, then your test statistic should have come out between these two values. If it didn't, and it goes into these little tails, that's what we call the critical region. See that?
Yeah.
These little tails here. If your p-value comes out here or on the other side, that means that the null was probably not true. And you get to reject the null. You get to get critical on its butt, right? That's why we call it the critical. Let me make these different colors. Let's make these green. Again, if your t-test test statistic comes out and is greater than +2 or less than -2, that means that the null is probably not true, and you got to get critical, right? You got to criticize. So, general rule of thumb: when you run your t-test, if it's greater than 2 or less than -2, you get to reject the null. And a little sidebar: there is no such thing as a negative t-score. People don't realize that, but we take the absolute value of the t-score, and they're always positive, because no matter what book you look at, there's no such thing as a negative t-score. But again, I don't want to get into a cat fight with any teacher that I'm not familiar with. So if she writes down negatives, you write down negatives. And I've seen it in a million different papers. They just write down, the t was -2.6. All that means is that they subtracted the big number from the little number. They could have reversed that. It doesn't make a difference, but I don't want to go on and on. All right, how's that?
Yeah, okay. Can you go over measuring effect size?
Effect size. Is it on this one?
I don't think so. It might have been the previous one.
Let's take a look. First of all, what is effect size?
I don't know.
Well, it's a good thing you got me, girl. I'll tell you right now. Hold on a second. Okay, there's... I'm thinking maybe this one. Z-scores, okay. Control. Effect. Oh, there we go. Now we're cooking. Hold on a second. Okay. Effect size is proof that whatever you did had an effect on whatever you're measuring. Okay? So let's take an example. Let's say you take 100 people with severe depression. 50 of them, you give them therapy, right? And after 6 weeks of therapy, you give everybody a depression score. So you get the 50 that did not have anything. They're the control group. They didn't get anything. And then you take the 50 that had the therapy. So if the therapy worked, the effect would have been lower depression scores. Is that clear? That's why we call it an effect size. An effect size is, all right, you might want to write this down. The effect size is the percent of the variance in the DV that you can explain by whatever your model is. So in the one we just did with 50 getting treatment, 50 not getting treatment, the effect would be for the grouping. The grouping was where the explanation of the variance in the depression scores is coming from. So the variance in the depression scores, right? Some people are really depressed, some people are not so depressed. So some people have low depression, some people have high depression. That is variance. And if the more of that you can explain, the better. That is called effect size. The percent of the variance in the DV that you can explain with your model.
Might be in this one. Power of a hypothesis test.
Power. Now, power, in a nutshell, all it really checks is your sample size big enough for people to believe your results? Power means that your sample size was large enough that you can, there's effect size. Power is basically sample size. In other words, it goes by many definitions. Power is the sensitivity of your test. In other words, is the test that you're running the right test to run? Is it sensitive enough to be able to determine if there was, is it sensitive enough that when you rejected a null, did you do it properly? Or not rejected, did you do that properly? But in a nutshell, power is, it checks on your sample size. The bigger the sample size you have, the bigger the power. Now, there is an ugly formula that I don't see here, but I'm not down to power yet. Power equals sample size times effect size divided by error. But I don't want to throw that at you because I don't think she's gone over it. But the main thing I would expect you to learn is the higher the sample size, the higher the power. The higher the effect size, the higher the power. Okay? The higher the error, the lower the power. And whenever you run any test in statistics, there's three things you should be looking at. First one is if it's significant or not, right? That's when you do all the calculations and you get a test statistic and you look up the p-value, and if that p-value is less than 0.05, you reject the null and say, huzzah, there is a difference, there is a relationship, significant. And if you don't get significant, stop, done, you go home. There's nothing left to do. But if you do get significance, the second thing you should look at is effect size. The bigger the effect size, the better. The larger the effect size, the more believable your results are. And then the last thing you look at is power. Your power has to be at least 0.8 or you will be laughed out of the statistics club. So you always want a fixed power of at least 0.8. That is, there's no questions asked. If you don't reach 0.8, then your results become questionable at best. But effect size ranges, it changes from test to test. So what does she say here? That is, okay, hypothesis test evaluates the significance, right? Okay, that is, determines whether there is not sample mean occurred from a treatment effect. Okay, the hypothesis, wait a minute, okay. The hypothesis test is influenced not only by the size of the treatment effect, which is effect size, but also the size of the sample. Thus, even a very small effect can be significant if it is observed in a very large sample, yes. because a significant effect does not necessarily mean a large effect, it is recommended that the hypothesis test be accompanied by measures of the effect size. So again, effect size. Cohen's d is the effect size for t-tests. There's another one used for t-test called eta squared, but not everybody seems to use Cohen's d. I personally think it's not a very good one, but nobody listens to me. But Cohen's d is basically a z-score. You subtract the treatment mean from you subtract the two means and divide it by the group standard deviation, which is exactly the same formula for a z-score if you didn't know. But now an effect size for Cohen's d, you subtract the means divided by the group standard deviation, both group standard deviation, and whatever that number is, that gives you your Cohen's d. If it's 0.2, it's weak. If it's 0.5, it's medium. If it's 0.8 or above, it's considered very strong. And again, you want a strong effect size. The bigger the effect size, the better.
Okay.
Oh, I hate these graphs. They're confusing. I don't want you to look at them. Turn your heads. So, all right, so here we go. So practice. So the average IQ stated by the government is 100, and the standard deviation stated by the government is 15. How do I know that? Because the letters representing them are Greek. A Greek letter represents population parameters. Okay? And then you take a sample of 25, and their average is 115. Oh, shit, you got a smart group. So you want the 4 tests, or the 4 steps of hypothesis test. And I also want the Cohen's d. So do you know what the 4 steps are?
No.
Subtract the means, divide them by the standard deviation. So 100 IQ versus 115. So it's 115 minus 100, that's 15, that's your numerator, divided by your standard deviation. Actually, it should be divided by the standard deviation divided by the square root of the sample size. Did I lose you guys?
Yeah.
I need a chalkboard. Wait, don't go nowhere. Please hold. I got another thing here. Open. T. Where's my T? T. A lot of T's in here. Let's use this one. Bam. Open. Just open your rat bag. All right. That is your t-test formula. Everybody see that? So our sample mean is what?
Is it the 100?
Remember, English letters represent samples. Greek letters represent parameters or population. So what's our sample mean?
I don't know, I can't see it on your screen anymore, so let me look at mine.
There it is.
115, yes.
So 115. What is, let me see if I can get these both on the same screens. All right, so there's that. So it's going to be 115. Oh, you rat bag. 115, that's your X bar, minus 100, divided by standard deviation, that's 15, divided by the square root of 25 is 5. Okay, so the numerator is 115 minus 100, that's 15. So 15 divided by, standard deviation is 15, divided by the square root of 25, square root of 25 is 5, so 15 divided by 5 is 3. So we got 15 divided by 3, that is 5. Does that make sense?
Kind of. Okay.
I know this is going a little bit fast, but again, I'm going to send you some links that it just walks you through this. So again, 115 minus 15 minus 100, that's 15 on top. Standard deviation is 15 divided by the square root of 5, that is 3. So we got 15 divided by 3, right? 15 divided by the square root of 5, 25 is 5. 15 divided by 3 is 3. So 15 divided by 3 is 5. So your t-test statistic is 5. It's 5, which is huge. That means that this mean here is 5 standard errors away from the stated mean. So therefore, you would reject the null. You would say that the IQ, the average IQ, is not 100 because it's your sample of 115 is 5 standard deviations, standard errors, because it's a sample, right? Whenever you divide the standard deviation by the square root of a sample size, that changes it into a standard error, not a standard deviation, but a standard error that's from a sample. Okay, so that's what you're doing. So you would reject the null, and you would say, no, the average mean is not 100. And the effect size is 15, again, it's going to be 115 minus 100 divided by 15. So the Cohen's d is 15 divided by 15 is 1, which is a very strong effect size. So in other words, you got indicated that Paradise Intelligence has the z-score is the z-score was 5 and the Cohen's d was 1.0. Again, small, medium, and large for Cohen's d. Now there's Cohen's f, there's eta squared, there's omega squared, there's a ton of different kinds of effect sizes. Remember that. And the numbers change on what's considered small, medium, and large. They change with the different tests. There's power. Right? In other words, power measures the sensitivity that your test will reject the null of the hypothesis when you're supposed to. But in real life, it's basically just checking that your sample size is large enough. So beta is, do you guys know what a beta is?
Probably not.
So alpha is your chances of making a type 1 error. I think she's got it up here somewhere.
Okay.
Which is always the same. Alpha is always 0.05. Right? Type 1 error is your chances of rejecting the null when you should not have. That is 5%. Beta, on the other hand, is the chances that you'll not reject the null when you should have. So this is 95%. This has always confused the shit out of me. It really has. But I think what it means is type 1 error or type 2 error, if you're going to make one, right? And it's not you, the researcher. It's never you, the researcher. It's just that your data is weird. Like you know, you reject. You're assuming that the average height of 30-year-old males is 7 foot tall, right? That's obviously false. But if you did a random, you know, you picked 10 guys at random and you took their average heights, and their average was, you know, 7 foot tall, which could happen. You could get, you know, if you pick 10 people at random, they could have all been, you know, Czechoslovakian basketball players. They could all be giant guys. And their mean would be 7. So you would not reject the null, right? When you should have. It's just your samples, your sample gave you a bad hand, right? You just got a bunch of tall guys. So again, type 1 error is when you reject the null when the null was actually right. Type 2 is when you don't reject the null when the null was actually wrong. This is, type 1 is always 5%. Type 2 is always 95%. They always have to add up to 100%. Don't ask me why. And then her definition of power is what I see in all these books. But to this day, does not make any sense to me. Okay, and there it is right there. No, not right there. Power is 1 minus beta. So in other words, whatever your beta is
You said that type 2 is 95% and type 1 is 5%?
correct. The chances of. So I'm not even gonna touch on this. So, but you know, power. This is true. Power equals 1 minus beta. Period. But I don't want you guys to put this on the back burner because again, the way that it's explained here is just confuses the heck out of me. I don't think it's going to do you guys any good either. Just remember, we always need a power of 0.8 or above. And then we have a power analysis. We use G-power now. Thank God. We run a power analysis to make sure your sample size is large enough. That's all we do, right? And, right, these are always related under power. Sample size, the bigger the sample size, the greater the power. Effect size, the stronger the effect size, the greater the power. Significance level, don't care. Power 1 minus P, type 2 error, probability of finding effect that is there. We can determine the fourth. Okay, increasing the effect size of sample, or I will increase your power. Okay, that's okay. That's caca. All right, let's do this last homework problem if you want to. We only got 10 minutes left. You want to do bolts? Ready, everybody? Can you see this?
Yes.
We're going to run a 1 sample t-test. So what are we testing it against? 4? Let's read the assignment. Okay. Follow the steps and submit the output file. Please note that bolt save can be found under week 4. So let's look at the book, shall we? Sample size is 15. You should examine the normality of the data before you run the t-test. Okay, so let's run the t-test. Oh, and there it is. The null hypothesis states that the average is 4. But the population average is 4. That's what that little mu looks like. The little u, pronounced mu. So that's what we're doing. So here we go. We're going to, first of all, we're going to check for normality. Analyze. Descriptives. Explore. Get in there, you. Explore. That's the only one in there. And we want plots. Unclick stem and leaf. Click histogram. And again, normality plots with tests. That is your main money maker. Click OK. And we should get a pop up here any second. Come here, you. Boom. There it is. So length. There's only 15. There's the average. There's the standard error. There's a competence interval. So this competence interval, they're 95% sure that the true mean of the data should be between this and that. And we don't care about the rest of this stuff. But ta-da, it is normal, right? Because the sig value for the Kolmogorov-Smirnov test did not dip below 0.05. So this means the data, it doesn't look normal, but it is normal enough to continue, okay? That's what that means. Part 2, we're going to go ahead and run the test. We're going to go to Analyze. We're going to go Compare Means. And this is a 1 sample t-test, right? 1 sample t-test. So it says, give me the variable. So it wants length. Very important, the test value. We're testing it against 4. And that's all there is to it. Don't even look at those. Don't ever look at bootstraps. Bootstraps are bad. These are for losers. Losers. So here's your t-test results. Again, the first box is just descriptive statistics. The number, the mean, the standard deviation, the standard error. So standard error. If I took the square root of n, if I took the square root of 15 and I use that to divide this by, I would get that number. That's how you get standard error. So here we go. The t-test statistic, negative 1.786. That literally means that the difference between the average of the length variable with all the scores in there and 4 is like 1.786 standard deviations away from each other, which is a lot. Okay, and because it's a two-tailed test, it is not considered significant. But if we thought that our sample was bigger than the stated mean or smaller than the stated mean, we could divide that by 2 and it would be significant. So that's how you play that game. All right, so I think she wants you to send in this sheet as well, right? Let's go back and look. So she does want the output file for this, okay. Please then, okay.
So would that be the same as just copying and pasting the tables and the graphs onto the Word document?
I would think so, but then she put it quite specifically. She wants to see the output file. Now, I'm going to send you everything we worked on today. So with the output file, you might want to, make like a copy and delete all the crap from the first one. So for like this last question here, your output file should have just this stuff on it, right? Where'd it go? Hold on. Your output file should have the test of normality and this, right? This should be on your last one. That right here should be question 3 only.
Okay.
But if she wants to see it all, I would say, go ahead, give it to her. All right,
Are you gonna send like what you recorded to us too?
Yes. I will do that right now. I'll clean it up and email it to you with a bunch of links to everything that we just went over.
Okay.
So you can read about it in the Hawks and watch the other videos. And hold on, did I just do this already? Hold on, save as. So how's Fresno? How's the weather up there?
Well, it was nice, and then it's getting warm again, and it's gonna get nice again this weekend.
Yeah, they're telling us it might rain here on Wednesday and Thursday. And what is today? I always put today's date on there. 09/23/2019. Here we go.
How's the weather in San Diego?
Oh, it's perfect. Actually,
I'm gonna be there next weekend for the AAPA conference.
oh really? I will make sure that the weather is nice for you. Actually, it's been kind of warm lately. Actually, it's just starting to go away. Summer's just starting to go away. It's getting back to its perfect 75 degrees every day kind of thing. But in the last couple of weeks, yeah, it's been getting like 95 degrees, which it's only happened for like a week or two. It normally happens a week or two, somewhere around September and August and October. But we're hoping that it's all gone now. So, did you know there's an APA thing here next week?
What APA thing?
What kind of APA thing?
It's the AAPA, it's the Asian American Psychological
Oh.
Association conference.
Down here in San Diego, huh? Nobody knew about that around here. So,
I did not know.
okay, I need to talk to you. Don't go too far.
I have to go pretty far right now.
All right, go pretty far. All right, so Summer, hold on 1 second. You,
Yeah.
when will I see you again?
What is it, Monday?
I need to talk to you guys about what they want us to do now. They want us to start helping with dissertations on the writing side, and they just don't have the manpower for that. And I kind of got yelled at about it. And
Why? I mean, it's not like we don't help out with dissertations.
you're
so.
supposed to help out with dissertations now.
Oh, there's not anybody else.
There's you for 4 hours, and there's Anna for 5 hours.
Oh.
And you guys got the most wonkiest schedules on earth. And I tried to tell them that, but man,
Well, what do they want?
they want you guys to work with dissertation students on the ones that need the writing help. And I fought
Yeah,
tooth
that's
and
fine.
nail. I went, no. But they said yes. So we'll talk about that later. Remember, 2 hours a week, max, anybody. Period.
Oh, for hiring?
For two, yeah,
Oh, for tutoring.
for tutoring,
I
yes.
thought it was 1 hour.
No, they get 2 hours a week. But I leave it up to you. I mean, you know, the writing part is so freaking boring. I don't see what you guys do.
Wait, why would they yell? It's not like we're not taking people that need help with
I
dissertation.
didn't want to open that floodgate. You know, once they find out, that's it for you guys. You will not have another free second to go. So, but we'll talk about it later.
Okay.
So block yourself off some time when I'm here. Let me know when, and I'll block it off on my schedule. Comprendes? Should I speak Spanish?
Trying to think when I will be here next. Yeah, no, Wednesday. You're always here on Wednesday, right? When I'm here?
Yeah. What
3:30?
time?
3:30 to 4:30?
3:30 to 4:30.
Yeah.
Or you block it off. I'm going to put you on my schedule. Me and
Okay.
you will make some plans.
Okay.
All right. Thanks, Anna. Ciao. Summer.
Yeah.
Where were we? All right. I'm gonna stop this video somehow, and I'm gonna edit it down just to the good stuff. I'll email it out to you tonight.
Okay.
And I'll send you some links with everything we went over, okay? But now a lot of this stuff, like the power and the effect size is important. Don't overly worry about power. The only time you have to worry about it is when you actually run a test, and SPSS automatically calculates your power for you, so you don't have to worry about that. So the important thing is figure out effect size, because that's going to be a lot. That's going to come back at you a lot. So, all right. Then let's check out, and I will talk to you guys next week.
All right. Thank you.
Thank you. Same thing. If you get any homework or something, email it to me. Let me know, and make sure I get the numbers.
Okay.
All right. Peace out. Bye, everybody. All right. How do I stop this recording?